This is Digital Lightwave sales training for internal use only. This is how to do SONET SDH demonstration on the NIC product. This, as I said, it's internal use only. It's not really for customers. And here we go. First thing you want to do in SONET SDH demonstration or any demonstration is a reset to defaults. Go to the System tab at the top. Go to Restore to Factory Defaults. And if you're in the SDH part of the world, you restore factory default SDH. SONET part of the world, restore factory default SONET. This will save a great amount of trouble because your instrument will always be in the exact same position when you start, so you won't have any surprises. Okay, we're going to go directly to the SONET tab. And if I'm controlling it remotely, I need to take control of the test set with the lock button here. I go press the little lock and exit. And now I'm in control of this particular test set. And first thing you do is point out, if you haven't already, the general structure of the user interface. Point out that on the left side of our screen we have these alarm and status indicators. It tells us on any particular test what's going on right at this minute. And we have a laser button here, laser on off. As soon as I get it configured to actually be using SONET, we'll see that come alive. The other thing to show someone are these series of buttons at the top: transmit, receive, results, test, and performance monitor. Transmit controls everything to do with the signal you're going to be transmitting. Receive sets up your test set to look for a particular signal. You're telling the test instrument what to look for, what signal, what rate, what mapping type, and so forth. And results is just what it says. It's going to display the results of our current test. Test has some specialized functions, which I'll show you shortly, and so does performance monitor. All right, now let's go into transmit, and I'll start going down the functions. And transmit settings is just what it said. It's the settings. It's the options of your transmit. And first button under settings number 1. There are a number of settings. There's so many that has to be in 3 screens. But under settings number 1, settings control is the first option. It's coupled or independent. That's important because if you press coupled or leave it on coupled, which is the default setting, if I make a change on the transmit, it automatically makes an identical change on the receive. So they're synced together. And that's the normal condition. But there are other conditions where you may want to set independent. So I can make a change on the transmit that does not get matched on the receiver. And pass-through mode is the next one. It's off or on. That means in pass-through mode off, the SONET or SDH transmitter will create a brand new signal, brand new payload, brand new overhead for testing purposes. In pass-through mode, it will accept an incoming signal on the receiver port and duplicate that signal through the transmitter port. So you can use the test set in an inline mode. And in some conditions you can actually make changes on the overhead, and you can add errors in the overhead payload in the pass-through mode. Now we're at interface, the next one here, and this one we're going to actually click, and I'm actually going to choose one of the interfaces. Let's do the top OC192 interface. I'll choose that one, and it's going to set itself for the OC192 interface. And now all the LEDs on the left now came alive, and the buttons are alive. I have laser is off as the first button. That's a button, not just a sign. If I click that button, it turns itself into laser is on, and it actually did turn the transmit laser on. And it tells me, there's more information here. It always tells me what my transmitter rate and what the wavelength is here. It tells me what our received power level is. And this next section is error alarm. It's, am I intentionally generating any errors or alarms? I'm not. And here's a test paused, if I had paused the test. Our clock is set for internal. And below here, all these LEDs mean what's happening with the current test. Since I restarted the test, what has happened? Green means good. Red in an LED would mean bad. Let me turn the laser back off to show you what that looks like. So I have red here, red for LOS, loss of signal, because the laser is off. And I have a summary LED here, which is section. Everything here is related to section overhead. Everything here is related to line overhead. Everything here is related to path overhead. I don't know if I should do any explanation of what a SONET section, line, and path are. Possibly, I should, but we can make that a separate. We actually should make that a separate training class all in itself. And nobody's particularly asked a question on it, so we're going to keep on moving. And next at the bottom, we have pattern sync. So when I'm sending information, I'm sending a payload in a known repeating pattern that the test set looks for to find out if it has any errors. And in that case, I have no errors if it's either white or green. Let me turn the laser back on. Okay, we're green, so I have pattern sync. That means it is receiving what it's sending. And if you see that some of the text is red as opposed to white, white is normal condition. Red means that's the history. There has been a failure of that particular item since the test was restarted. And if I press restart now, my timer, before I press restart, I want to point out the timer here, lapse time. It's been running for 2 minutes and 33 seconds, 34, 35. If I press restart, two things happen. My timer goes to 0 and it starts counting again. And all the red text turns back to white text. So this is what a perfect test looks like. It's been running for a few seconds now. Nothing has gone wrong. It's all green LEDs and white letters. Okay, and the next item underneath the interface is mapping. And it has all the applicable mapping types to a SONET OC192 that this unit is optioned for. We can really choose anything for our example. To make it a nice simple example in the beginning, I'm going to choose STS192C, which means that there's one payload only in the OC192 signal. Click that to make it nice and simple. And in that case, this next button has no function. If you'd like to show this, we can show this to the customer by changing mapping type. Let's change it to STS48C. And that gives me 4 payloads in a single OC192. I hope that makes sense. And then I have to choose which one of the 4 am I going to be transmitting and receiving on. So I'll just choose a number between 1 and 4. It says max value 4, min value 1. I choose just one of those. I go OK. Okay. And then I come down here to, not going to necessarily go in sequence. I'm going to more of a logical sequence. Next is payload. So I have this payload. What am I going to put in it? These are pseudo-random bit streams of different sizes defined by standard. It pretty much what the numbers mean is how many strings of zeros and ones does this particular pattern have. And it doesn't really matter what we use for the demonstration. 31, I believe, is the default. It is the default, so we can leave it on 31. There also is a user-defined button. If I press user-defined, then I get to type in a 32-bit value of my own choosing. I can choose binary, put it in ones and zeros. Anything you want for 32 bits long. I can do it in decimal numbers, or I can do it in hex. Anything you want, just like that. And that becomes our new payload. It's the payload that I created. That's what's being sent repeatedly in the payload. And then background pattern sets up what am I going to have on the other 3 payloads. Because as I said, in this STS48C, there are 4 of them in an OC192. I'm only sending my main payload, and I'm going to be receiving for the test purposes on 1. But on the transmitter, I have to send something in the other 3. That's what background STS pattern is. Background pattern is the same series of choices. I can put anything. I can duplicate what's on the test one, or I can put any other pattern I want in those 3. Okay, and next I have clock reference. Clock reference lets me do, most common, if the test set is looped on itself, is internal. For your testing purposes, if you're demonstrating it to a customer, you've looped it back on itself optically or electrically, internal. That's all you need to know. It has its own clock. It will use its own clock, perfectly fine. If you're actually connecting to a network, you're connecting to a live network for testing purposes, you use recovered. You just choose recovered, and it then will look at the incoming SONET signal, and it will match the transmitter to the incoming SONET signal. So therefore, it's automatically synchronized with the network. And bits, sets, and all these others are external clock sources. They're separately connected to the test set, not by the SONET input, optical or electrical, but by a particular connection. Bits in this case is a 1.544 megabit all ones signal, and sets is a 2.048 all ones signal, 2.048 megabits all one signal. Basically a DS1 signal or an E1 signal. And that can also be used, either recovered or bit sets is used for connection to an actual network so that your test set becomes synchronized to the rest of the synchronous network. And the same thing for these others. These are going to be very rarely used outside of any laboratory application. Mainly what you need is internal, recovered, bits and sets. And for your loopback test, just demonstration, we're going to leave it internal. Then we get into set number 2. There's more to learn about a clock, and this is actually a selling feature. So this is and it may be dull so far, but I'll get to the actual selling, what's unique about ours. As we go along, I'll show you a few things that are unique about our test set. This line frequency offset is an important function because I told the test set in the other screen to use the internal clock. I could have said the recovered clock, the bit sets clock. Now I'm going to tell it, okay, I don't want you to use that internal clock exactly. I want you to take that internal clock and I want you to go 1 part per million higher rate. You see that line frequency offset is now 1 part per million. And I'm going to jump over to receive for just a minute. I go receive sig, which means signal, and it tells me some information about the incoming signal. It tells me the frequency, and it's telling me the line frequency offset received. It's telling me that it's 1 part per million higher than what it expected. Also tells me optical power. We'll get to that other. See, hope that makes sense. Now here's the unique selling feature, is I can actually do 100 parts per million. So I can do 100 parts per million too fast or too slow. And again, it shows 100 part per million here. And I can do minus 100, plus minus 100. Okay. Now, not all test sets do this. Most test sets do this. But it's actually very important, it can be an important feature to your customers that they may not know about. It's not all that commonly used in testing, but it actually is quite important to do this as part of a testing program. It's a stress test. It proves what will happen in their network if they have an element that is off frequency. General rule in SONET and SDH is that all the equipment has to be within 20 parts per million. So they should be able to tolerate 20 parts per million. Well, with ours you can stress it much further than that, all the way up to 100 parts per million. So that was a selling feature. Go back to 0 on that one. Initial laser setting is more of a safety matter. That means when the test set is powered up, do you want it to come up with the laser in the off position, which is default, or in the on position, which is the laser is always on, or restore previous state, which means that if the laser was on before it was powered off, it will come back to on. And it's a bit of a safety matter, really, in case somebody might be splicing or using a fiber scope on the fiber. You don't want them to unknowingly have power on it. Any choice is fine. Just show the customer they have that choice. And this is part of the overhead. SS bits in the H1 label. It's part of the H1 byte in section overhead, and it indicates whether this particular signal is SONET or SDH. when I'm using SONET, it's going to default as SONET. There may be cases where you need to fake the incoming equipment. You may need to tell the incoming equipment this is SDH in order to have the equipment accepted. So you have that capability here. Just change it to SDH, and it looks like, to the incoming equipment, it looks like an SDH signal. And path signal label, again, it's something in the overhead that you can change. It tells what type of mapping do you have in this particular signal. And it's naturally going to be set to match our payload, but you can also use any of these if you need to. The customer needs to know that one. And synchronization status is another overhead setting. Our test set doesn't really care what it sends. This indicates the quality of the clock signal that's in use. And the default is sync trace unknown. Fine. Actually, it should be, to be correct, it would be a stratum 3. You click stratum 3, and it would actually tell the incoming or the rest of the SONET or SDH network what the clock quality was of the signal that the test set is putting out. And if you used an external timing source, you could actually use one of these higher, one stratum 1 or stratum 2. Hope that makes sense. It's just the test set doesn't care what it sends. It's just going to send this message, and that will have various other effects in the network. Like the network may be able to use this as the source timing or not, depending on how you put this label. The main thing for you is that you can set it. You show the customer that you can set it. Trigger in is something that I don't think you're going to run into in the field. It actually is an external port on the test set where you can have a certain thing happen if a voltage is received on that trigger port. When a voltage is received, you can have it restart the test or insert an error. Don't think that's going to be a commonly used feature, but you can show it as a possibility. And tandem connection overhead processing, it's enable or disable. I'll tell you a little bit more about tandem connection processing as we get to that. Okay, and settings number 3. These are two things that are very rarely used. I'm not quite sure why they're grayed out in the condition I have here. Both order wire and datacom channel are part of the overhead. Order wire is a voice channel that can be added because if you were in a place where you didn't have a telephone, you could use an order wire, and you actually are talking just one voice channel across the same fiber that the SONET signal is using, SONET or SDH. And our test set actually requires a special, we use the word dongle, a special adapter. At least all the new modules require a special adapter so that you can use the order wire. We literally have never sold one, so we know that that's very uncommonly used. In the days before cell phones, they were order wire was much more commonly used, but now that everybody has a telephone everywhere, it's almost unheard of. And datacom is some more additional information, more data that can be sent on the SONET or SDH overhead that our test set could add or not add for testing purposes. Again, not a big use. All right, now I'm going to go down to, I'm going to go actually over to receive and show you some of the same things on settings. I don't have to go in quite such detail because we've talked about most of them already. Settings control is the same as transmit. If I said coupled here, it would actually make it coupled in the transmit. And interface, same group of settings that we had for transmit. Mapping, same group of settings. Which STS-48C we're going to drop and do our testing on, same one. Again, I have a payload, but here payload doesn't mean what am I going to send. Payload means what am I going to look for on the receiver. And now I have a couple of alarms I can set if I want to. Power low threshold, if I want to set that, for now, for example, my power is minus 6.82. If I wanted to know if the power went down a little bit, I might set it for minus 7, for example. So then if the power happened, let's see, let's not do that. Oh, I can't set it that high. It goes to minus 10. Minus 10 dBm. Okay, so now if my power went below 10, then I'm going to get an alarm. I have a power low alarm that will come up on the alarm screen. And I'm just going to clear that out. How to clear it out? 0. No, that's not it either. Oh, I see. Actually, I don't know how to set that. And out of frequency threshold is another thing I can set. So as you saw, I changed the clock. I did 1 part per million and 100 part per million. I can set this. I can set an alarm on the incoming signal data rate as well. I can set, say, 20. If it goes more than 20 above or below, then it's going to give me an alarm. And trigger out is similar to trigger in. There's an actual external port on the test set. I can have a voltage appear on that port when any of these happen. A bit error, for example, or any particular type of error I want it to see. Or for every frame pulse, I can have a voltage appear on that port. Again, these are features that not all customers will use, but they may want to know they're there, so run through and show them. Then the path label alarm reporting, I can make it on or off. If I turn it to enable, then I get what is the expected path signal level. I can set it for any particular mode, and then an alarm will occur if I don't get that exact path signal I'm expecting. And this one is a trace message alarm reporting, enable or disable. I can have a particular overhead byte called J0 or J1 set. J0 is part of section overhead, J1 is part of path overhead, and these are trace messages. And what they do is they're very useful for the customer. It's another thing you should show the customer. Pretty much all test sets do this, but the customers will value you for explaining it to them, what it does and how it helps them. J0 is a message in section overhead, and you can actually type in, you can use a keyboard to, and here we're setting the expected one, because user-defined 64-byte. I can put in a message, such as this is, I can spell it all out, this is the circuit from New York to Tokyo. Anything you want. You can put a circuit ID number up to 64 characters. And that's what it's going to look for. And what the customer can do with that is they can make sure that they're testing on the system and the fiber that they believe that they are. J0 is part of section overhead, which is terminated basically every time it's converted from optical to electrical. That J0 is going to stop. So there's only one J0 on each SONET signal. So that would be to determine which fiber. You know, you're in a big central office with hundreds of fibers. If each one of those had a J0, you could put a test set on it and look at exactly where that J0 came from. You can put a location like a city, you can put a rack number, you can put a channel number, anything you want on the J0 from the equipment or from the test set. And the test set will tell you if it doesn't match what you're expecting. And J1 is similar, except it's part of path overhead. And path overhead is not terminated every time that it's converted from optical to electrical. A path goes from the beginning of a path to the end of a path. If we were testing from New York to Tokyo, the J1 would start in New York, would travel all the way through to Tokyo, and anywhere along the line you could see if that J1 signal arrived. Would help a lot in troubleshooting. That's a very useful feature that our customers can use. And I have SS bits alarm reporting, so I can have it look for those. SS bits was the timing bits that we saw. Oh, I'm sorry. Where do I set when it's going to be? If I enable it, I'm not actually sure where oh, there it is, expected SS bits. So which of these, sorry, it's not timing, that's what I said wrong. SS bits are the SONET SDH bits, so I'm going to determine is this SONET or is this SDH. So I can look at if I'm expecting a SONET signal, I set it for SONET, and if I get anything but that on those two bits, then I'm going to get an alarm. And again, tandem connection, error processing alarm, it's disable or enable. If I enable it, then I have another trace byte, similar to J0 and J1, I have another trace byte here that I can set. Same thing. I can set it up for what I expect to see. So these are all nice features that customers have asked for. They're good selling features. And on setting number 3, I have more of order wire datacom channels, which are grayed out in a condition I'm not quite sure why. You may run into things like this in your demonstration. That's a good reason to practice demonstrations in advance, which I didn't happen to practice on set number 3 yesterday, so I'm not sure why those are grayed out at the moment. And go on back to transmit. I want to show you a couple other things there. SOH, section overhead. This is combined actually. These three on the top are called section overhead. These three on the bottom are called line overhead in SONET. In SDH, this would be regenerator section and multiplexer section. And what I can do here, this is showing me the entire overhead, the entire section and line overhead of SONET. If I want to make a change in one of these, all I have to do is click on it and then type in the new value of that overhead byte. Each of these is just a byte, 8 bits. That's all. That's as easy as change. That's how easy it is to change overhead. It's something to show your customers how easy. This is the setup of the overhead. Many of these you can't directly change here. B1, B2, those are error calculations. They are set in every frame by the test instrument. It's an error calculation. That's how they detect errors. The H series is SONET or SDH pointers, which I'm going to talk a little bit more about when we get to pointers. They're automatically set by the test set. J0, which we talked about as a trace, that's automatically set. Oh, not automatically set, but it's set down here. You press J0, and then I can go user-defined 64 byte. I want to put just put the word test a couple of times. Enter. And you'll see down here this is what it's sent on the J0. But any of these other bytes, anyone that's not grayed out, I just hit it. I type in any value I want it to be. I can do hex FF, which is all ones. That byte is now sent as FF, which is all ones. This one is D5 is what I changed it to. J0 is test, test. Now if I go over to receive, because my test set is looped on itself, so I'm sending a signal out of transmit, back to receive. If I go to receive, section overhead, you'll see that the J0 did detect test, test, and the D5 is D5 byte is 5.5, like I said it would be, and D8 is all ones, which is FF. Hope that makes sense to everybody. Nobody's asking any questions. You certainly can, if anything doesn't make sense. And we go back to transmit. POH is path overhead, and this is, it's more overhead. It's the path overhead. It goes with any, as I was saying, if you test all the way from New York to Tokyo, this is the path, this is the part of the overhead that travels all the way. And again, I said any of the overhead bytes by just clicking on one of them, typing in the value that I want it to be. Very simple. And this has two traces. It has a J1 trace, which looks the same as the other when you're setting it up. And this is, let's do J1. That's all. That's what that's going to send. And tandem connection trace is another trace. Same thing. The user defined there. Okay. And again, if I go to receive, path overhead, then I see my J1 message and anything that I happen to have changed. That was my Z3 that I changed. I think. Yeah, Z3 that I changed. Okay, back to transmit. Now, pointer, we do have some interesting features on pointer. I hope that all of you have a general idea what pointer is. Pointer is a mechanism that allows, let me say it in a different way. The SONET and SDH systems, the networks, are designed to be synchronous. Everything is timed to the exact same clock. But what happens if they aren't really exactly timed to the same clock? There needs to be some compensation for something that's just not quite perfect. That just not quite perfect is the action of pointers. Pointers allow some of the signal to be a little bit off, and the pointer is a value assigned so that the receive section knows how it's off. It knows where to look for the payload because its timing is a little bit off. Okay, so a normal condition is to have no pointer adjustments. Well, we can create a condition that's abnormal. This frequency offset button, I can create a condition. I can go 100 parts per million too fast or 100 parts per million too slow on the payload. So I'm going to go 1 part per million. I'm going to tell my payload to run faster than the rest of the frame. And what happens is now I have PTR key, which is path pointers, constantly occurring. And this pointer value is a number. It goes from 0 to 782. And that's a pointer value. It just tells where in the frame the receiving equipment is supposed to look for the signal. Now this is important to your customers because it's something they can use to stress the network as part of their testing. And 100 parts per million is a very, very extreme test. It wouldn't really be wouldn't even be a requirement for a network to be able to handle that. But the test set has to be able to stress it as far as they want. That's much further than they would ever need to. And I can also do, well, let me go to receive pointer and show you what that value looks like as it's received. Or results pointer, rather. Sorry. Results pointer shows that I have negative justifications because my payload is running faster than the rest of the frame and has to do constant negative justifications to keep it working and in line. You will notice there are no other errors, even though my transmit payload is not running at the correct rate as it's supposed to, because this is a synchronous network. It's actually perfectly fine. There are no errors. Nothing else is wrong except the pointer is doing its job at 100 parts per million. And it tells me negative justification for that many seconds, or for that many justifications, and then for how many seconds have I had pointer justifications, as long as I've been doing it. And yeah, go back to transmit. Okay, I'm going to set that back to normal, 0. Now, I have two things here. I said the pointer value goes from 0 to 782. I can, if I want to, just arbitrarily set a new pointer value. Just tell it that's going to be its new pointer value, and the transmitter will set the payload so it starts at that point. This NDF flag, new data flag, it tells, without getting into a long discussion, I don't know what I can tell you about new data flag. Every time a brand new pointer value arrives at the incoming SONET equipment, it could be an error, there could be a bit error in the pointer value. Like if in one frame it's pointer value 13, the next frame is pointer value 712, that's not a normal condition for a pointer to change that much in one frame. So the SONET receive equipment will actually ignore extreme pointer value changes unless they come with a new data flag, which would be something like if you changed payload types. Your SONET equipment, SONET or SDH equipment, would put a new data flag in it to tell the equipment, okay, I know it's an extreme change, but it really is right, and go ahead and make the change. And what it does in the test set, if I go new data flag, yes, and make an arbitrary change, like that, do it a couple times, with new data flag on, I go back to results, pointer, it tells me it got 3 new data flags. And if I go turn data flag off, then I should be able to make as many changes as I want arbitrarily without getting any more new data flags. See them? Over here I did not get new data flags. I still have only 3. But when I made the change, it caused bit errors, because it didn't automatically make, the receiver knew not to automatically make the change. So that's a normal condition for that is yes. Doesn't matter what this value is, it's an arbitrary value. Now I can do what's called pointer sequences here. I can do, we'll leave it on single now. With that I can, INC is increase or increment, either one. DEC is decrease or decrement. So I go increase pointer, notice pointer value now is 4, increase pointer, it's now 5, 6, each one of these is a pointer adjustment. I can decrease it just by 1. These are tests that your customers may want to do. And then pointer action, I had single. These others are particular sequences defined by the standards that your customers are going to look for. So I'm not going to explain what each one of them is. Basically, you choose one of these and just press. Let's just do that. I'll explain exactly what they are. But your customers, if they need this, will know exactly what that is. They can do bursts of 5 pointer justifications at a time. How many milliseconds do they want to do between bursts? and you just press increment and it starts. Okay, so these are pointer sequences. Mainly you want to say, look, here's how you explain it to a customer basically. Look, we have these pointer sequences. And you show these different sequences. You do not need to know exactly the details of what the sequences are. Okay, well, we're 45 minutes into this already, and I didn't even get to nearly as much as I wanted to show you, but I'll move a little faster. Okay, next is APS. We're still on transmit. APS lets you choose a value for K1 and K2. This is a very unique selling feature. And K1 and K2 are bytes used in automatic protection switching control of line switching equipment, or in the SDH world, I suppose it would be called multiplexer section switching equipment. And I go new item, and I choose some value for K1 and K2. If I want this one to be that value, and I want it to be that value for 23 frames, I go update, puts a line there for that one. I go new item. Okay, the next time I want this particular value to be that, and I want it to be that for 15,000 frames, 15,500 frames. Update. And then if I press start, it'll go through this sequence. It'll do this value for 23 frames, it'll do this value for 15,000 frames, and I can put any number of new items there. This can be important for testing, especially research and development. It's very important. Okay. And now I'm going to get, and then on results, APS, I can see the received value. See, it really did it for 23 frames, just like I told it to do. Okay. And then error alarm is pretty important. I'll show you a new selling feature here in our remaining few minutes. Choose what error type to insert. For example, let's do bit errors. And nothing has happened yet. Just clear the count out there for you. Okay. Nothing has happened yet. I didn't insert an error yet. If I go to results, I see error summary, errors, all 0. I've had no errors at all. Scan tells me, I created that one. But anyway, go to errors. I have no errors whatsoever. I told it error type bit. So now if I press error insert, I should get 1 bit error. And there I did, 1 bit error. If I press it again 3 times, 1, 2, 3, get a bit error each time. And this error result shows me the average rate, which is the bit error rate since the test started 39 seconds ago, or however long it says on elapsed time. Current rate is the rate in the last 1 second. Okay, I go back over here to error insert. I did error to insert bit. If I go error insert rate, I can pick a particular rate, like 1 times 10 to the 5th. Go to results, and just restart it to get the number right. All right, so it's running right at 1 times 10 to the 5th, average and current, because it's happening right now. I can also do something that most test sets can't do on my error insert rate. If I go user defined, I can be a little more detailed in what I want to set. For example, I can go 1.3 exponent 5th. 1 times 3, 1.3 times 10 to the 5th instead of 1.0. I want to find out a little more exactly when a certain thing happens. Okay. And alarm, I'll turn that back to off. And alarm generated next is more of an on-off. If I choose an alarm type, alarm indication signal line, it turns on the alarm indication signal line until I turn it off. Turns it on, turn it off. Okay, and that's it for transmit. Nothing else on transmit. And to receive, I've showed you several things already. Next, the one thing I didn't show you, which is a new feature on our products, is capture. With this, I can capture overhead bytes. This is a fairly new feature. Most of you probably have never seen it. It's only on one of the newer software rates, one of the new software revisions. Byte select, I tell it which byte of the overhead do I want it to capture. We'll leave it on A1. I can choose any of these bytes. And slot number, within an OC192, there are 192 slots. That same A1 appears 192 times. So which one of them do I want to capture? Let's do 1. And the capture trigger can be, what happens to make it capture. If I get any of these notices, that's when it starts to capture. If I go manual, it's going to start as soon as I tell it to start. But you also may want it to, if you ever get a bit error, you want to find out what happens in the next few frames after that bit error. If that makes sense. That triggers a very unique feature. Let's put it on manual. Okay, and then how many bytes do you want to capture? 255 is the maximum. And you just go capture. And it's going to capture that many values, or 255 frames of that byte, number A1. Now let's do a byte that changes all the time. Let's do an error byte, for example. So let me do that. H, that's a pointer byte, that'll do it. Okay, capture that one. Oh, I'm sorry, let's do a different one. Let's do B. Capture. And see, the B changes in every frame. So I get a different value coming in on all my captured bytes. Very useful, very new feature. SIG you saw already. Signal status is tells me the frequency, the line frequency offset received, the optical power, and the STS pointer frequency offset received. Meaning that if we put a, which we did, I didn't show you the result here, but when we put a frequency offset in the pointer, which created that pointer adjustment, we would have seen it here as well. And it tells you just very directly, the test set can tell you if you have a signal that's not synchronous with the rest of the network. And then on results is pretty quick to show. We only have 9 minutes left. This took a little longer than I thought to get through these, but we will end on time. We always do. So results. On error alarm, scan is the first thing. It's going to show me every possible error. If there were nothing wrong right now, it would show no errors or alarms. Now, I'm going to go back to restore to factory defaults and get rid of those. That's a shortcut if you're in the middle of your demonstration. You have a number of items that have shown up. You're not quite sure where you turned them on. You're not quite sure where they are. You don't want to confuse the customer. You can just get rid of them. Evidently, oh, well, I have no laser turned on. And now let me get back to set my interface again too. Pretty quick. We're clean green. We will restart. Okay. No errors or alarms. That's more of a normal condition. That's what you expect in a test. That's what a customer wants to see on every test. Scan just tells me everything. Errors tells me every kind of error that's possible. What's the average rate? What's the current rate? Alarms tells me every alarm type that's possible and for how many seconds did I have it in the current test. PTR, which we already looked at, tells me how many justifications I have on the pointer. Event is useful. That tells me everything that happened since I started the test. It always has a start test at the beginning. Let's cause some errors and alarms here. We'll see what happens. Everything that happens gets a line of information, and this just accumulates. And this is how somebody can go back later and find out exactly when something happened for troubleshooting purposes. My test started, then I had a loss of signal. It started at this time, it was over at this time. I had another one, severely errored frame. Anything that happens along the way. And if things are happening very fast and you can't see the change but you want to see it better, you can press the pause button. It doesn't stop accumulating information, it only stops showing it so that you can see it. And resume it goes back to showing it again. You can make it ascending or descending, so the start can be at the top or bottom. And if I stop a test, then there's going to be an end test variable. And you can print this, you can save it, which I'll show you more about saving tests. Our next class next week is actually going to be Ethernet, but the one after that is a little more about testing features like printing and saving results, that sort of thing. Very useful. And next is APS, which is automatic protection switching. I showed you already, K1 and K2 byte over what happens in different changes. Large LEDs just takes the same information that's over on the left side here, these alarm and status indicators, makes them a little bit larger so that you could see them a few feet away or from across a room. You can see if this is green or red much easier than you can on the left side. Okay, and then graph. The function of graph is essentially the same as event. It's going to show you everything that happened since the test started. The difference is it's going to be in a graphical format. We've had some errors since the test started. Let's change to sample rate 1 second. Yeah, we should be able to see some of these. So we did have a loss of signal at certain times, and it's updating every 1 second, so it's kind of moving along. We can change the scale. We can go up to, we'll go to 24 minutes, and it'll be a smaller scale. Anyway, we're going to see what happened during the current test, but on a graphical format. Same information as event, basically, but just presented in a graphical format. Okay, and you can save and replay these graphs here with Save Graphs. Okay, then under Test, a couple of unique features. Setting number 1 is how you set the time factor of a test. Defaults is continuous, so when I start a test, it runs forever until I stop it. I can also set it for particular periods of time. 24 hours is a very commonly used one. I can go user defined. I think I can go to 99 days, 99 hours, and 20. Actually, I don't know how many minutes. Nope, can't do that. Hours can exceed 23. What did I say 99 for? Days can exceed 28. Okay, it's making me wrong. Let's see if I can at least do 59 minutes.